So welcome to our second talk in our lecture series in summer 2021 at the Monday Colloquium of the Deutsches Museum, which we have organized and will hold for this semester together with cooperation partners. The lecture series is titled Thinking Machines, History, Present and Future of AI, or in German, Maschinendenken, Geschichte, Gegenwart und Zukunft der künstlichen Intelligenz. The cooperation partners are the European New School of Digital Studies with Jan-Hendrik Passot, who has held the Professorship of Sociology of Technology there since last year, and the Philosophy of Computing Group at the Warsaw University of Technology with Hajo Greif, who is Research Assistant Professor there. I am Rudolf Seising, and I'm leading a science history project on the Deutsches Museum, at the Deutsches Museum on the history of AI in Germany. With that, I turn the floor over to Hajo Greif first.
Szanowni Państwo, witamy na naszym cyklu wykładów o historii, filozofii, socjologii i sztucznej inteligencji. Nazywam się Hajo Greif. Jestem filozofem na Politechnice Warszawskiej. I continue in English for now in order to be better understandable. So the idea for this series was born when the three of us were still based in Munich. As it turned out, Jan moved to the border between Germany and Poland, to Viadrina, and I moved even further east to Warsaw University of Technology. And our idea back then was to try to create, to develop an integrated humanities perspective on artificial intelligence, like history, philosophy, and social studies of science. Of course, we back then, 2 years ago, 1.5 years ago, we thought about a live series that would be held in Munich. As we all know, things turned out otherwise. We first postponed it, hoping to be able to host this instead of summer 2020, in fall 2020, but COVID just wouldn't go away, and it didn't until today. So many months ago, we decided to move this online, and this is why we are here now. So welcome to you all. And now I hand over to Jan.
A very warm welcome also from me. My name is Jan Passot. I'm third in a row of the organizing team. And I just want to use this opportunity to remind you that there are many other great talks also coming up after today's discussion with Stephanie Dick. We will see Shannon Weller, Wolfgang Biebel, Harry Collins, Vincent Müller in the next weeks, and we will end up this lecture series in July with a panel discussion with Virginia Dignam, Christian Kerstig, and Matthias Spielkamp, a panel discussion that might even take place at the Deutsches Museum, but probably be also held online in this form. And allow me a few words on the organization of the discussion. Later on, we are collecting questions through hand raising and the Q&A option of this webinar function. The webinar function sadly doesn't allow us to see you all. We only see you in list, but we are aware of your hand raising and questions, and we will do our very best to hand them in well, symmetrically, basically. So if you're raising a hand, Hajo will later on give you the floor to ask the question personally and allow you to do this in audio. If you just typed it into the Q&A option, I will take up these questions and forward them either to Stephanie, or if they are complicated and I would think that it's better that you ask them yourselves, we also might give you the floor of asking them yourself. You can start writing these questions into the Q&A also while the talk is going on. We'll try to sort them maybe into a few categories so that we can make this discussion as concise as possible. And we are really looking forward to a lively and thrilling discussion of today's talk by Stephanie Dick. I'm giving back to Rudi to introduce our guest for today.
Thank you, Jan. Today's, sorry, is maybe the wrong one. Sorry for that. not working. That's the wrong one. Just a moment. Okay, today's talk in our Thinking Machine series is called Making Up Minds, and our presenter is Stephanie Dick. Stephanie is a historian of computer science and mathematics, primarily in the United States in the 20th century. She was junior fellow of the Harvard Society of Fellows and received her PhD in the history of science from Harvard University in 2015. She has been an assistant professor in the Department of History and Sociology of Science at the University of Pennsylvania since the fall of 2017, and currently she is advisor for the Lauder Center Global Knowledge Laboratory at Pennsylvania University. Stephanie's research interests concern mathematics and computing in the post-war United States, and in particular artificial intelligence and automated reasoning. She published in ISIS and in the IEEE Annals of the History of Computing. And here you see her work in 2011, Aftermath, the work of proof in the age of human-machine collaboration, and machines who write in the IEEE Annals of the History of Computing. Her book, which will appear soon, will explore early attempts to automate proof and new formulations of mathematical reasoning and knowledge that were developed in tandem with them. This book will offer a historical answer to the question, what is thinking if a computer can do it? By way of answer, Stephanie will recover and reconstruct how different communities theorized human cognitive faculties with automation in mind. In her lecture today, she asks how two human cognitive capacities, thinking and knowing, have been redefined in the context of early approaches to automation in mathematics with an eye toward the computer. With clear reference to the fact that these capacities of thinking and knowing have been denied to many people in Western history, colonized people, enslaved people, women, Stephanie Dick wonders how these capacities have been attributed to machines. And with this, the floor is yours, Stephanie.
Thank you so much, Rudy, and thank you to Hayo and Jan as well for your organizing, not once, but twice, first an in-person series and now an online series. I'm also really grateful to Cynthia for your technical support and to the different institutions who are supporting this lecture series. I'm very honored to be a part of it. So every time somebody says that a computer has done something, that it has accomplished a given task, that it has recognized a face or diagnosed a disease, that a computer has won a game of chess, that it has proved a mathematical theorem, that it's written a poem, every time the task in question has been redefined. It has been transformed into something that a computer can do. It has been put into the terms of the machine, translated into data structures and programming languages, into computer operations. It has been remade with the computer in mind, its affordances, its limitations. And it has also, that task, been put into terms that computer programmers and engineers know and understand and can work with. There is no automation without this kind of transformation. Automation is the act of putting things into the terms of the machine and into the terms of the people who control and operate and develop it. And all of my work basically has been an exploration of what those redefinitions, those translations, those acts of accommodation, of actually accommodating the computer involves. And I've been particularly interested in what happens when human faculties like intelligence or intuition, reasoning or knowing have been put into the terms of the machine. How have those faculties been understood in new ways with the machine in mind? And as Rudy mentioned, I'm just about finished my first book manuscript, which is called Making Up Minds, Computing and Proof in the Post-War United States. And it is about attempts to automate mathematical theorem proving, mathematical reasoning, and mathematical knowledge in the second half of the 20th century. And it is about what happened to those faculties as they were abstracted and extracted from people and put into the machine. We are remade in more ways than one alongside of our technologies, especially those that are meant to capture, to reproduce, or to reflect back something essential about the human. As Lucy Suchman put it in 2006, I've always loved this, quote, "Just what it means to be human-like and how the boundary between humans and non-humans is correspondingly drawn and redrawn is of course one of the matters in question. AI and robotics involve a kind of doubling or mimicry in the machine that works as a powerful disclosing agent for assumptions about the human. The human is not a stable category in the story of technology, but rather humanness is a relative term. In Western hands, humanness has been defined through history against a great many others. Humanness has been defined relative to angels, similarities and differences with angels, also through similarities and differences perceived between humans and animals, and also humanness has been defined relative to all manner of machines, both real and thought experimental, which all four of these works explore in a very longue durée historical sense. But humanness is also a category that has done great violence. Western Europeans and Americans in service of colonial ends also defined humanness in opposition to other people, those that they wished to colonize, to control, to enslave, to exclude, to exterminate. And that violence was often justified by a dehumanization of the other people in question. And over the course of the 20th century and into the 21st century, computers have become one of the central others according to which the idea of humanness is defined through perceived similarities and differences. A great many stories have been told about computers that feature claims about what is human or inhuman about them, about what is machine-like or not machine-like about people. And in the field of automated mathematics, my primary area of focus in the book, different kinds of human ability, capacity, contribution, and labor were used to sound out the limits and the possibilities that different researchers perceived in a modern digital computer. To give you some sense of that, here are snippets of the anthropomorphic language that was used to suggest what kinds of contributions computers would be able to make to mathematics from the 1950s and 60s. Some researchers suggested that, at least in principle, everything that a human mathematician does could eventually be automated and that computers would become like coworkers or colleagues or mentors. Others thought that computers would be more like assistants or students, or how they perceived graduate students, capable of carrying out all kinds of work and problem solving, but not without expert guidance. Yet others believed that computers would only ever take on rote and mechanical tasks and would be more like servants, assistants, or slaves, and more on that later. In this talk today, I want to share with you two stories, two accounts of the human and the machine, and in particular, two accounts of the human reasoning faculty, that faculty seen as so central to intelligence, to knowledge production, to law and social order that emerged in the earliest years of artificial intelligence research. And I want to explore how these two very different visions of the human informed very different research programs in early computing. So this is a tale of two reasons. The first will be, I expect, a familiar story to many of you. I will begin by talking about the theory of the human and of human reason and intelligence that informed Alan Newell and Herbert Simon when they developed their logic theory machine, an inaugural AI program that produced proofs of logical theorems from Principia Mathematica in the mid-1950s. And the second story is from a far less well-known researcher from this field, a Chinese-American logician by the name of Hao Wang. He also developed a set of computer programs in the late 1950s that did the same thing, basically. They also produced proofs of theorems from Principia Mathematica, but according to a very different vision of the human, of the machine, and of the intellectual history that informed those ideas. And by exploring these two accounts of the human together, we can see how research agendas and automation approaches encode theories of the human and human-machine relationships in such different ways. And I propose that there's a lot to be learned from how Wang's critique of Newell and Simon's work in the 1950s and 60s, which anticipates a lot of critiques that humanists are now articulating about AI. And there's also a lot to be learned from Wang's rejection of some of the core assumptions that Newell and Simon made about people and that proliferated as their approach to AI became paradigmatic over the second half of the 20th century. So the logic theory machine was developed by Newell and Simon while they were working at the Rand Corporation in the 1950s. And for those who are unfamiliar, Rand was founded at the end of the Second World War and was supported by the US Air Force in particular, and had been given the mandate to explore what future global wars were going to look like and to develop strategies for winning them. But how could they know what those future wars would look like? The simple answer, of course, was that they could not. There were so many uncertainties about what new technologies would be developed, what geopolitical regions and states would be involved, the when, the where, and the how. None of this could be known. And a lot of research at Rand can be interpreted as developing ways to try and model and predict and optimize warfaring without actually knowing any of those details. And AI was born in that crucible of defense problem solving. At Rand, researchers tended to move away from material reality, geopolitical specificity, into the realms of abstract models and techniques that they hoped would apply to whatever those future wars ended up being like. And one of the core set of techniques that was developed at Rand for doing work of this kind was called systems engineering. And this was the view that you could abstract away from the world all kinds of systems. Governments could be seen as systems, companies could be seen as systems, transportation could be a system, the weapons on a plane could be a system. And the goal was to not study the specifics, but rather to focus on the relationships between the parts of a given system, what mathematical relationship obtains between the parts of a system, what information travels between them, rather than thinking about specific materials and people and institutions that might constitute it. So even if you couldn't know the when, the where, the how of the future wars that would be fought, you could know, they believed, how to strategize for any war by modeling the systems that are involved and looking for ways to optimize their performance. These works up on the slide here are some of the important historical foundations that track the genealogy of systems engineering, as well as the many roads by which it traveled from the defense establishment into domestic governance and planning. And my second book project actually explores how systems thinking shaped the early introduction of computers to domestic policing in New York State in the 1960s, but that is a story for another day. So Newell and Simon were working within and helping to shape the systems engineering view of the world in the abstract, where material specificity mattered much less than the relations of parts and the circulation of information. And Newell and Simon famously came to believe also that the human mind and the modern digital computer could and should be studied as systems as well. And more than that, that they were the same kind of system. Simon called them species of the same genus, namely information processing systems. So both the mind and the modern digital computer were systems that took symbolic information as input, manipulated it according to a set of rules in order to output the solution to a problem, a judgment, a decision, and various other valences of intelligent behavior. This was the theory of intelligence in which the material did not matter. It could be brains, bodies, computers, corporations, hybrid organizations of humans and machines, as long as you had a system that could take in symbolic information and be set up to manipulate it according to the right set of rules, you had a system that would be intelligent. It's an abstract model of the thing. And actually, Newell and Simon went so far as to say that until you had a model of the information processing involved in a given intelligent task or behavior, you hadn't understood it. Understanding the human for them was a project of identifying the rules for manipulating information that they believed were at work in human intelligent behavior. They wrote, quote, "We wish to emphasize that we are not using computers as a crude analogy to human behavior. Our position is that the appropriate way to describe a piece of problem-solving behavior is in terms of a program, in terms of certain elementary information processes it is capable of performing. This assertion has nothing to do directly with computers. Computers come into the picture only because they can, by appropriate programming, be induced to execute the same sequences of information processes that humans execute when they are solving problems. Hence, programs describe both human and machine problem solving at the level of information processes. They were advocates for abstraction, for a vision of intelligence and its constituent processes and faculties as independent of materiality, of embodiment, of machinery. And they were advocates for this deep similarity between humans and computers at that abstract level, at a distance from the vantage point of the systems engineer. They were the same. The logic theory machine was their first attempt to actually identify and then automate a set of information processes that they believed was responsible for a domain of human reasoning. And in particular, the logic theory machine was meant to prove theorems from an early 20th century text in mathematical logic, Principia Mathematica, that was written by two English mathematicians, Alfred North Whitehead and Bertrand Russell, around the turn of the 20th century. And in Principia Mathematica is laid out a system of deductive logic. So a set of axioms or premises and a set of inference rules or inference principles that you could apply to the axioms in order to deduce the true consequences within a formal system. Whitehead and Russell hoped, in fact, that their logical system was powerful enough to allow you to, at least in principle, deduce all of the significant theorems from the different branches of mathematics. This turned out not to be possible, but that was the idea that motivated the project. So in order to develop their computer program, Newell and Simon first needed a theory, a model of what it is that humans do when they prove mathematical theorems. What are the information processing rules that need to be followed in order to reproduce that intelligent behavior in the machine? And for their model of human logical problem-solving behavior, they turned to a Hungarian mathematician by the name of George Polya, who fled to the United States in 1940, and with whom Newell took all of his classes when he was an undergraduate in mathematics at Stanford. So in addition to his research mathematics, Polya was deeply interested in mathematics pedagogy. And he believed, contrary to a number of mythologies or idealizations about mathematics, the mathematicians don't just deduce consequences from axioms in hopes of deriving interesting, true theorems. Mathematicians do all sorts of things. They start from something they want to prove and they work backwards looking for related problems. They experiment with cases, they look for analogies, they build models, they look for counterexamples. Mathematicians have a lot of tricks for going about problem solving and theorem proving. And Polya, importantly, didn't think that those tricks were esoteric secrets, hidden and tacit, but rather that they could be identified, made explicit, formalized as rules, and then taught to students in order to make them better at doing mathematical problem solving. He wrote in 1954, "Certainly let us learn proving, let us learn how to deduce consequences from axioms, but also let us learn guessing." And he called those ways of guessing, those tricks for mathematical problem solving, heuristics, after the Greek word for to find. It's a navigational term. And this was a perfect model of human problem solving behavior from Newell and Simon's perspective, because they wanted a set of rules that captured human problem-solving behavior and that could be translated into a program and run similarly on a computer. And the logic theory machine was structured around two heuristics in particular. The first was that it worked backwards. Rather than starting with the axioms of the logical system and then deducing consequences looking for theorems from Principia. This would in fact have produced an exponential explosion of data and had been ruled out as a possibility earlier in the 1950s. The logic theory machine instead worked backwards. It started with the theorem from Principia, a logical proposition that it wanted to prove, and then it would generate a set of subproblems that, if they were true, would lead in one permissible inference step to the desired conclusion. And then it would develop a set of subproblems that led to those subproblems in a single permissible inference step, and so on, in hopes that eventually you would produce the axioms themselves as subproblems. And if you did, you could then run the relevant branches of your tree backwards and have a nice deductive proof of your proposition. This didn't work all the time. In fact, it provably fails in a number of cases. And Newell and Simon knew that this was not a holistic model of human logical problem-solving behavior, but they thought it was a good start, and that the automation of heuristic rules was the key to reproducing intelligent human behavior in the machine. That heuristic approach was taken up by AI practitioners in a number of other domains and proliferated well into the 1980s. This was the model of human problem-solving practice that Newell and Simon wanted to automate. But models and abstractions don't compute. They actually aren't enough yet for computing. In order to get a model like this to actually run on a computer, it had to be implemented, had to be translated into the terms of the machine. And even though they thought materiality was somewhat irrelevant, they had to reckon with it nonetheless. They had to find a way to execute these heuristics on the Joniac computer at Rand, and it's something like 52 kilobytes of memory. So now they needed to translate these heuristics into computer memory, into computer operations, and in fact, they ended up developing a whole new programming language and a new set of data structures with the computer, not the person, in mind. They called them linked lists and list processing operations, quite inhuman structures and processes that implemented this high-level vision of theorem-proving behavior. So what was meant to be a very human, precisely human, in fact, model of behavior became quite inhuman and alien in the transition to implementation. And throughout my work, I have advocated that historians and critics and theorists of computing not just direct their gaze at the abstractions and the algorithms, at the models or the screens about which so many stories are told, but to look at what actually happens when the abstraction meets the machine, when the machine has to be accommodated. We cannot accept or assume the irrelevance of materiality, embodiment, practice, especially where the researchers we study are trying to erase it. The logic theory machine becomes quite inhuman in its implemented form, which Newell and Simon thought was irrelevant. But crucially, neither Newell or Simon had the requisite experience with computers and computing machinery that was necessary to implement their model on a machine. For this, they had to enlist a third collaborator by the name of John Clifford Shaw, who he came to Rand to work in the numerical analysis department, later renamed the programming department after fighting in the Second World War. And Shaw recounted to Pamela McCorduck, who spoke before me in this series when she was doing her essential interviews of early AI researchers, that they worked in the basement. It was the only space large enough to accommodate the computers, and they were large and loud and hot. Shaw recounts that they called it a sweatshop. They worked without shirts on. They packed boxes of punch cards between machines. It was very loud, hot, physical space, quite in contrast with the realms of abstraction, where Simon thought the real work was being done to theorize, model, and implement intelligence. It was in the programming department or the numerical analysis department where people got their hands dirty, quite literally, with computing machinery, implementing the abstract models and calculations that were developed elsewhere at Rand. And with Shaw's help, the logic theory machine became a running program on the Joniac mainframe, but it had taken on a quite inhuman form of computer operations and data structures that people would really struggle to work with. And I don't have time to get into the details of that implementation today, but I can refer you to a piece I wrote some years ago about the implementation of the logic theory machine and the ways that logical propositions and the rules of inference and heuristic problem solving were implemented by translating them into quite inhuman modes of operation and representation that were developed in order to accommodate the machine that Newell and Simon so fervently proposed was secondary, even irrelevant to the question of intelligence. Their vision of reasoning as rule following, as an abstraction from material reality, became paradigmatic for AI. But there were also those who, at the time and from even within their community, rejected both of those premises, and among them was the Chinese-American logician Hao Wang. Wang was a philosopher and specifically a logician, but over the course of his career, he became deeply critical both of analytic philosophy and of logic, in part because he felt the abstractions in which they trafficked were just fictions. They were being treated as real, but they bore so little resemblance to realities that they were abstracted from that they weren't very useful. He was concerned that the abstractions at the heart of analytic philosophy, logic, and early artificial intelligence did not grab a hold of enough reality to honor or to guide the messy and contingent experiences of embodied human and political life. Wang entered philosophy, as so many do, to study what he called the human dilemma, but found little in the abstractions of analytic philosophy and logic that resonated with his experience of it. Wang proposed that Newell and Simon and those who approached the problem of AI as they did had made a fundamental mistake. They had believed a fiction told about the human mind that had led them mistakenly to see the computer as the same kind of thing. He wrote, quote, "Logicians had worked with the fiction of man as a persistent and unimaginative beast who can only follow rules blindly, and then the fiction found its incarnation in the machine," end quote. It was an understandable mistake, Wang thought, because human minds had been so often idealized, abstracted, and modeled as rule-following entities, especially by his colleagues and predecessors in mathematical logic and analytic philosophy, who had long sought to reduce human reasoning to a formalism, and who had in turn associated embodiment and emotion with irrationality, irrelevant, or worse, an impediment to right reasoning. One of the crucial tenets of these theories of the mind was a presumed universalism. The same rules of reasoning were thought to be at work across problem domains, across cultures, across nations, across minds, and across humans and machines that were programmed to be intelligent. However, it has been a core area of study and a foundational claim of historians of science over the last several decades that this purportedly universal faculty was in fact reserved primarily for educated white European and American men who simultaneously denied the capacity for right reason to many people. Women, colonized people, people of color were often characterized as irrational, unreasonable, superstitious, for various scientific reasons, physiologically incapable of the mental discipline that was required for right reasoning, this purportedly universal faculty. Relatedly, many logicians, especially in the English tradition, working around the turn of the 20th century, like Russell and Whitehead, but also George Boole, claimed explicitly to be engaged in a descriptive project. They wanted to reveal and describe the rules of reasoning that were at work in the human mind. Newell and Simon continued this project by proposing that their research first revealed the rules that were already at work in human intelligent behavior, and then translated those into a program that could later run on a machine. However, these various scholarly works suggest in different ways that these were in fact normative projects, even coercive ones, in which the universality of reason was created by the disciplining of mental acts and the rejection of nonconformity as irrational, unreasonable. But artificial intelligence researchers in the 1950s believed the fiction that reasoning was a universal across people, across problem domains, and so on. This theory of reason, especially in the hands of AI practitioners, as we saw, was also inherently abstract. It didn't matter what material system enacted the rules, a human brain, a human body, someone from America, someone from China, a company, a hybrid organization of humans and machines, so long as it followed the right rules, the system would be reasoning, intelligent. Wang, however, had a different theory of human reason. He rejected both the abstraction and the universalism assumed in these philosophical fictions of the mind. Human thinking, he believed, was contingent, individual, historical, and embodied. It was shaped by the specific experiences and circumstances of the thinker. He wrote, quote, "A particular act of recognition or reasoning depends on one's genes, the history of one's mind and body, some essential relation to desire, even race, class, sex, and many other factors. Of most of these factors, we have at best an imperfect knowledge and understanding," end quote. Human reasoning could not be reduced to a universal formalism because each person's reasoning faculty develops uniquely according to numerous, only partially understood factors. Very recently, race and technology scholars like Yarden Katz and Andre Brock have explored how universal often just means white. Wang did not couch his critique of universal theory in a theory of universal reason in a theory of race, but there are some important parallels. Brock writes that, quote, "Whiteness is itself signified as universal, raceless, technocultural identity. As white folks' communications, letters, and works of art are rarely understood as white, instead they become universal and understood as communication, literature, art," end quote. Whereas Black art, Hispanic art are different as, or specified as such, are not assumed to be universal in the same way. Similarly, reason, as the mechanism thought central to knowledge production, truth claims, and other intelligent behaviors, was fashioned in mathematical logic and again in early artificial intelligence as universal, but was in fact, as Alison Adam has explored and others, was distilled from some of the most white and male dominated domains like mathematics and chess. Early practitioners of AI, themselves overwhelmingly white and male, like Newell and Simon, imagined that all they needed to do to understand intelligence was to observe themselves through techniques like introspection or reasoning aloud, and that this would suffice for the identification of a universal reasoning faculty. Katz writes, quote, "Like whiteness, AI aspired to be totalizing, to say something definitive about the limits and potential of human life based on racialized and gendered models of the self that are falsely presented as universal," end quote. Wang's rejection of universal reason in the 1960s was grounded in part in his training in materialist philosophy in China, where he grew up and completed his first 2 degrees, and also in his engagement with both Marxist and Maoist thought during the Cold War. Wang thought that Marxism, unlike analytic philosophy, was actually well suited to the study of the human dilemma, because rather than abstracting them away, Marx emphasized materiality, history, labor, and embodiment, and because he offered a theory of social change, a guide to action. Marxism was a useful philosophy. Wang wrote, quote, "Although there was much that puzzled me in Marxism, I felt that I saw a comprehensive philosophy unifying thought and action in a way that I had not before considered possible," end quote. And it was this desire to bridge thought and action, to make philosophy and abstraction useful, to cultivate a philosophy that honored and guided real life, that brought Wang to computers in the first place. He saw in the modern digital computer not any similarity to humans, but rather a deep difference. Quote, "The human inability to command precisely any great mass of details sets an intrinsic limitation on the kind of thing that is done in mathematics and the manner in which it is done. But the superiority of machines in this respect indicates that machines, while following the broad outline of paths drawn up by man, might yield surprising new results by making many new turns which man is not accustomed to taking. We are, in fact, faced with a challenge to devise methods of buying originality with plodding, now that we are in possession of slaves, which are such persistent plodders," end quote. This was not artificial intelligence. This was buying originality with plodding, which may in fact be a better descriptor of a lot of what gets called artificial intelligence these days and back then. Whereas Newell and Simon had recognized an incarnation of the fiction of the intelligent human mind as a rule-bound reasoner in the computer, Wang recognized instead the abstract idea of the slave. inhuman, rule-obeying, mindless, also a fiction that was of course untrue and violently so of actually enslaved people. But industrial capitalism, we might say, was predicated on both fictions, on the universality of reason, according to which manufacture, management, and bureaucracy relied on the one hand, and on the machine-likeness of the factory worker or the enslaved person who would be disciplined and punished to behave as machine-like as possible. Wang saw both fictions incarnated in the machine and wanted to know what could be done with that technological manifestation of that intellectual history. What inhuman feats might the machine accomplish? What epistemic possibilities might be opened in tandem? In the late 1950s, Wang was lecturing in philosophy at both Harvard and Oxford, the two centers of analytic philosophy and logic. He had just completed his PhD in philosophy at Harvard in 1946, which he did under Willard Quine. But given his growing dissatisfaction of these fields, Wang started spending his summers at places like IBM and Bell Research Lab and the Burroughs Corporation, where he also developed a set of computer programs for proving theorems in Principia Mathematica. In his critique of analytic philosophy, Wang was particularly disappointed by the fact that not even mathematicians seemed to have very much use for mathematical logic. Wang and his colleagues were in the business of developing and exploring and studying formal systems that were thought to be foundational to mathematics, but that not even mathematicians could easily or willingly or readily make use of. He wrote, quote, "A common complaint among mathematicians is that logicians, when they are engaged in formalization, are largely concerned with hair splitting. It is sufficient to know that proofs can be formalized. Why should one all take all the trouble to show exactly how such formalizations are to be done, or even to carry out actual formalizations," end quote. Most of what mathematicians produce, as many of you are, I'm sure, aware, are not comprehensive step-by-step proofs of theorems, but they're partial, they're incomplete. They are sketches of a proof, seldom comprehensive formalized proofs themselves. Russell and Whitehead famously, or maybe infamously, didn't even get around to proving that 1 + 1 is equal to 2 until more than 200 pages into Principia Mathematica, just to give you a sense of how cumbersome it was to work within these formal systems. But Wang thought, what if these formalisms could be made more useful for actually doing the work of mathematics? What if there is more potential in these abstractions than we had otherwise even known to look for? That is what he wanted to use computers to do, to take abstractions and logic in particular and to make them more useful tools for doing the work that mathematicians are interested in doing, for actually solving problems and proving theorems. So his approach to proving theorems automatedly from Principia Mathematica was not based on any theory of how humans do it, but was rather based on a fundamental result from a branch of logic called proof theory, namely Airbrand's theorem, which was proved by a French logician, Jacques Airbrand, in 1930. Airbrand's theorem offers a mechanism for proving theorems in one branch of logic that is described in Principia Mathematica called the predicate calculus, that includes existential quantifiers like there exists or for all, in terms of a simpler branch of logic with which Principia opens, called the propositional calculus, that doesn't have those existential quantifiers. And the theorem is as follows. For any statement P from the predicate calculus, that more complex branch, the theorem gives a process, a method for producing a corresponding infinite series of statements in the propositional calculus, that simpler branch. And then the theorem states that P is a theorem if and only if, for some number n, the first n of those s's connected by the or operator into what's called a disjunctive series is a tautology, meaning that it's true no matter what values are substituted for S1, S2, and so on. So one way to search for a proof in principle would be to test whether S is a tautology for n = 1, n = 2, and so on. And if P is a theorem, you would eventually find a tautology and, by Airbrand's theorem, a proof of P. But crucially, Airbrand's theorem was never meant to actually be used to actually solve any problems or prove any theorems in the predicate calculus. Because even in really simple cases, you might have to check trillions of cases before you find a tautology. You can calculate an upper bound sometimes on n, but even still, this is not a tractable way for humans to go about proving anything. And worse, of course, if P is not a theorem, you would go on forever, never knowing if the next case might be a tautology, and it would never be. Airbrand's theorem is a particular kind of result. It is a statement, an abstract statement about the relationship between two branches of logic. It is an in principle method, but not a practical method for actually proving theorems. People couldn't apply this in any obvious way to actual theorem proving. But Wang thought maybe the computer could. And so Airbrand's theorem was a set of resources that he came to with a new set of questions and with the computer in mind to see if he could identify in it new information that would allow the computer to make use of this relationship in ways that people couldn't. He wanted to put logic to work to see if it could be made useful in a new way with computers. He wanted to bridge thought and action, abstraction and practice. And Wang, over the years he was working on this project, developed a quite remarkable way to do this. One that shows us that logic isn't, in fact, this universal deductive turning of the crank, but that it can actually be mercurial, that there's more to be done with these formal systems. Logic leaves a lot of space for creative rethinking that gets left out of the fictions we tell about these formal systems. Logic was not some guarantor of a universal truth, but rather a set of systems whose character evolved alongside a set of questions that researchers came to ask of it. And it also that evolved alongside the different and changing materialities and practices of mathematics, including the introduction of the computer. So Wang's program for proving theorems from Principia Mathematica was called a method of pattern recognition, through which he exploited a structural property of Airbrand's theorem that hadn't previously been given much attention and may not have been relevant in order to program his computers to look for proofs of statements from the predicate calculus. The secret that he discovered, and I won't say too much about this, but I have an article coming out sometime in Osiris that covers the details, but the idea behind the program was this. The S's in question, because of how they are generated out of P, usually share some variables. So the same variable might appear in S1 and also in S8. And remember that for this disjunction to be a tautology, you only ever need one S to be true for any given variable assignment. You need one S always to be true no matter what values are assigned, but you only need one for any given variable assignment. So the computer, under Wang's direction, set out to look for the different ways that these S's structurally could be made false, and in fact, to try and falsify all of them at the same time. But what if, because S1 and S8 share a variable, every time I try to make S1 false by assigning falsifying values to its variables, I force S8 to be true? And what if it's like that in every case? For every possible falsifying value assignment, you force some S then to be true. That's precisely the kind of structural characteristic you want for a disjunctive tautology. That's the basic intuition behind the program anyway. So Wang developed a method for looking at the finite number of ways that these S's could be falsified, and then checking if those falsifications always forced truth out of some other proposition because of their structures and their shared variables. And you could actually use these structural properties to prove theorems in the predicate calculus, albeit proof by contradiction, assuming no tautology was possible, and then looking at how attempts to falsify all the S's actually create a tautology in some cases. Wang called this a method of pattern recognition, but these were not patterns that people could see. These were algorithmic patterns that the computer could check. In his archive, his notebooks are full of these empty tables that gesture to the method without being able to perform it. This was not a reproduction of human practice, but rather Wang came to Airbrand's theorem with a new perspective, one grounded in what the computer could do. And he found in the theorem new structural information about logic and about the relationship between these S's that had previously not been appreciated. Turned out to be a very powerful method. It proved way more of the theorems from Principia Mathematica than the logic theory machine, and in considerably less time. But Newell and Simon rejected this as not the kind of thing that they were trying to do. Their goal was not actually to prove theorems. Their goal was not actually to build tools that mathematicians might want to use for solving problems. Their goal was to reproduce a theory, a fiction, a model of human problem-solving behavior in an automated form. And whereas Newell and Simon wanted to recreate human practice, Wang wanted to keep human creativity and ingenuity and understanding and knowledge central to working with computers. Buying originality with plotting was only possible when you came with fresh eyes to old tools, asking new questions, opening up possibilities, finding or creating previously unseen possibilities in our knowledge for doing the work we want to do in the world. This was not about replacing the human knower, but rather encouraging a creativity and ingenuity in people to try and bring ideas into more meaningful contact with practice, with experience, with action. It was the same desire for thought and action to be aligned, the same desire for abstraction and philosophy to do justice to what we know, rather than abstract away until the world and the human become unrecognizable, that brought Wang to the study of computers and to the study of Marxist philosophy. In 1956, Wang was sailing between New York and London, between Harvard and Oxford, but was stopped because he was found to be transporting undeclared electronics components that exceeded the limit after an unknown colleague of his reported him to the FBI, saying that he was planning to transport electronics to China for the purpose of nuclear arms development. That was not at all the case. None of the components were controlled as nuclear secrets. All were just very standard parts for computers. And he was in fact transporting them for a friend, a fellow Chinese American who was going back to China and who feared, because he had already been subjected to the cruelties of McCarthyist era surveillance, that he would not be able to bring them himself and would be unable to continue his research once he left. Wang was also found at that time by the FBI to have a number of Marxist pamphlets and literature in his suitcase. And this image of him sailing between Harvard and Oxford, the two most analytic philosophy departments on the planet at the time, with a suitcase full of computer parts and Marxist literature, really captures something fundamental about Wang's experience of the Cold War world. In the early 1970s, following the rapprochement between the US and China, Wang was among the earliest visitors to return to China. And when he came back, he became a public defender of both Mao and Maoist domestic philosophy and policy. He penned many letters to the editor defending both Mao and Marxism and urging the study of Marxist philosophy in America. He was cited by the Honolulu Star Bulletin, his keynote address at the East-West Philosophers Conference in Honolulu in 1973, as saying, quote, "Wang said Chinese Marxism applies philosophy to transportation, weather forecasts, treating broken backs, keeping vegetables fresh, delivering letters, and raising peanut yields." He contrasted these examples to Western philosophy's abstractions and contradictions, end quote. This is what Wang wanted: ideas that worked in the world, ideas that applied to the human dilemma, ideas that were a guide to action, rather than the abstractions, fictions, and contradictions at the heart of analytic philosophy and logic. Wang eventually abandoned his commitment to Marxism and Maoism once some of the realities of life in Mao's New China had emerged over the 1970s and 80s. And at the end of his life, Wang reports having been quite depressed and heavy of heart, that maybe none of our knowledge, none of our philosophies, none of our theories and models of history or theories of change and of the human dilemma could do justice to the lived reality, could actually serve our needs on the ground. In 1993, just 3 years before his death, he wrote, quote, "From 1977 on, a Chinese glasnost reevaluated a certain number of the views of the Cultural Revolution and earlier. In particular was the revelation from private conversations and literary works of many concrete facts about which most persons before had no idea. After coming across such information, this is about realities of life in China, I began to doubt my own most recent views. I felt that due to my deeply rooted and stubborn patriotic thinking, I had imagined certain facts that were grounded in wishful thinking. Upon this foundation, I had erected a logical construction that was really a castle in the sky, end quote. I think Wang's late life reflections are instructive, both in their humility, quite different to the hubris that traffics then and now throughout AI discourse, and in his disappointment. I know in my own communities, a lot of scholars, especially right now, are feeling devastated and furious and frustrated that our scholarship, our ideas, our critiques, our histories, our theories of change, our models, that they don't and maybe can't do the work in the world in the way that we had hoped. They did not serve and have not served as guides to action that honor or ameliorate the human dilemma, because they have become too disconnected from the lived experiences, the needs, and the realities of that human dilemma. Somehow all our knowledge and models and theories and histories did not spare us some worst case scenarios of the pandemic, for example, and in other both direct and indirect ways, our knowledge has failed to answer the questions that it raises for us in the world. Wang lamented the fact that the abstractions and fictions of philosophy tended not to be useful because they were so disconnected from human experience. He wanted philosophy to be a guide to action, to inform and guide human and political life. Wang's alternative theory of human reasoning, not as universal and rule-bound, but rather as individual, as contingent, embodied, historical, that theory, I suggest, came with an alternative vision of knowledge as well. So many Enlightenment thinkers and their intellectual descendants suggested that our knowledge must be the product of that universal reasoning faculty that we know is not universal. Anything produced otherwise would not, in fact, be knowledge. But if that reasoning faculty is a myth, a fiction, and quite inhuman, in fact, as Wang believed, then we are in trouble. The message is that our knowledge is only as good as we can be inhuman in its production. Knowledge is what follows the turn of the crank and the suppression of so much of what human life and experience actually involve. That vision of knowledge and knowledge production is a recipe for alienation in which people may not see themselves, their sense of their own life and experience, represented in the knowledge that is meant to serve as a foundation for scientific, political, and social order. And I think we are witnessing the effects of that alienation across social and political life in a lot in recent years, reaching what Lorraine Daston recently called ground zero empiricism, in which, contrary to the confident claims from technocrats and experts about how knowledge should be produced and circulated and how we should act on it, people are realizing that, quote, there is no settled script for how to go about knowing, end quote. Or as Henry Cowles has noted, quote, such metaphors figuring knowledge as a tradable good to be produced and circulated bolster our sense that science is solid, a stable thing that buttresses reasoned debate. But what if it isn't, end quote. And I'm deeply grateful to Henry for a longstanding collaboration around this set of questions about reasoning and knowledge. And his recent book on the scientific method is one of the definitive accounts of how these factors play out. The demand that people separate their minds from their worlds, from their bodies, from their realities, from their experiences, from their communities, in order to produce knowledge is not only alienating, but may in fact be a root cause of some of the deepest social, political, and psychological suffering of the 20th and 21st centuries. Wang's story offers us both indications that this was never the only way that we might proceed, and that alternative ways of thinking about knowledge and the human have always been available, and that they bring with them very different visions of what our technology is for and what its use is for making worlds and for building knowledge. So I'll stop there. Thank you so much. I'm really looking forward to the discussion.
Thank you, Stephanie, for this very exciting talk. I liked it very much, and I'm looking forward to receive your book.